Okay, so let's continue for our chapter of kinetic theory of gases. So let's continue with the root mean square speed of molecules. So root mean square speeds of molecule. Speeds. So what is actually meant by the root mean square speeds of molecules? Okay, so this is the root mean square. The definition of root mean square speeds of molecule is actually defined as the square roots of the mean square speeds. Mean square, okay, QUARE, mean square speeds. Oops, mean square speeds of molecules. So this is actually the definition for the root mean square speed of molecules. Okay, so let me erase this one. So we're still in the parts of the root mean square speed of molecule. Okay, as we discussed from the previous video, by saying that the pressure of the ideal gas equation is actually P is equal to 1/3 rho C square. So from this formula we are able to derive it into the root mean square speed equation. So let's say I have 1 mole of gases. Consider 1 mole of gases. Oops. Okay, so P is actually equals to 1/3 rho C square. So the rho for the 1 mole of gases is actually equals to capital letter M, which is the molar mass for the gases, 1 mole of gases. Since 1 mole of gases is equal to the molar mass of it. Okay, so this is the molar mass. So divided by the volume of 1 mole of gas. So this M is meant by the volume of 1 mole of gas. So this is the C square. Alright, so let's say I move this 3 and Vm into this side. So we got 3 PVm. So it's actually equals to mc square. Okay, so we know that PV is actually equals to nRT. So from in this case I have the 1 mole of gases, so this is actually PVm is equal to RT. So what I got is actually equals to PVm is actually equals to RT. So I have mc square. So this C, what I derive, the final answer what I got is actually 3RT over M, capital letter M of course. So this will be square root since this is there's a square here. So the root mean square speed we got for this formula is actually the square root 3RT divided by M. Okay, so this is the formula. Okay, so how about the relation between the root mean square speed and the temperature, which is here, and the molar mass of the gases? So the relation we can define, which is directly proportional to the square root of the temperature, and also at the same time is inversely proportional to the molar mass of the gas. So this is the relation which is quite important for us to to determine the root mean square speeds. Okay, so we have done for this part, so let's just move on to the other parts. Alright, so let's move on to molecular speed distribution at different temperature. So molecular speed distribution at different temperature. Okay, so let's say I have a so let's say I have a axis here. Okay, so this is the number of molecules. So this is the molecular speed. So this number of molecule varies with the molecular speeds. Okay, so let's say I have a curve which is here. So this so there's another curve for me which is here. Oops, sorry. This curve should be lower. Alright. Okay, let's say I denote this as T1 and this one is T2. Okay, so we know that the central tendency, which is here, so what we define here is actually the most probable speeds. So as for here, which is down a bit, the number of molecule is less than the number of molecule which have the most probable speeds. So this is the mean speeds. And here, finally, oops, there is no space. Okay, so let me approximately note it here. So this is the root mean square speed. So let me write it down. This is the most probable speed. Okay, so I spell it wrongly. Most probable. So this is most probable speeds. So this is my mean speeds. So the mean speed is have the less molecule compared to the molecule that has the most probable speeds. Okay, so the VR finally is the mean square speeds. Okay, square speeds, which is much more higher than the mean speeds and the most probable speeds. Okay, so let's say this T2 is actually more than T1. Okay, so at T1 we can see that they have the most probable speeds and the mean speed and finally the mean square speeds. Okay, so when let's say I increase the temperature, from T1 to T2. So as we can see that from T1 to T2, the curve of distribution, so this curve is actually called Maxwell wait, let me check again. Maxwell-Boltzmann distribution curve. So Maxwell-Boltzmann distribution curve. So this curve is what we call Boltzmann distribution curve, by the way. Okay, so let's say I increase the temperature from T1 to T2. As we can see that the curve is actually flattened. So why is this so? This is because, okay, when the temperature increase, so where should I write it? Okay, so let me write it here. So let's say my temperature increase, so the kinetic energy gained by the gas increases. So this causes the speeds, the most probable speeds, to be shifted here and here. So this will be my new most probable speeds, and so this also followed by the mean speeds for my new mean speeds, and finally my new mean square speeds, root mean square speeds, sorry. So when the temperature increase, so I repeat again, so the temperature increase from T1 to T2, so the curve is actually flattened, so the number of molecule which is at this point will be decreased. So as we can see that ignoring the curve for T1, so let's observe for T2. So at the T2, the molecules that has this most probable speed, mean speed, and root mean square speeds, the number of molecule has this respective speeds is actually decreased to this point. This is because the new most probable speeds and followed by the mean speeds and the root mean square speeds has shifted to this shifted to the highest speeds due to the kinetic energy. Okay, so never mind. So due to the kinetic energy gained by the gas increase, so this followed by the speeds of the gas will also increase. So this is how we determine the curve for Maxwell-Boltzmann distribution curve, which relates the number of molecules of gases and the molecular speeds, okay, at different temperature. So this we have done for this parts. So let's move on to another parts. So let me erase all this. Alright, this one as well. So this one as well. Okay. Oops, why does it can be erased? Okay, never mind. So let's move on to the degree of freedom and the law of equipartition of energy. Oops. Okay. degree of freedom and the law of equipartition of energy. Partition of energy. Okay, so let me draw a line for these topics. So let's start with the degree of freedom. Degree of freedom. So what is actually meant by degree of freedom? So degree of freedom is actually defined as the number of independent ways of the gas molecules to acquire kinetic energy. Okay, so this is the definition of degree of freedom by saying that there is a number of independent ways for the gas molecules to acquire kinetic energy. So let's move on step by steps. Okay, so let me just erase this one. Alright, so let's move on to we are still in the parts of degree of freedom. Okay, so there are three types of degree of freedom. Not degree of freedom, should be the motion of the gas molecules. Three types of motion can be described for the gas molecules. So as for the first one, we have translational motion. So this translational motion, we know that is actually relates to the linear motion. So as for the second one, we have rotational motion. So this of course relates to the rotation of the gas molecules. So as for the third one, we have vibrational motion. So this vibrational motion is the vibration between the gas molecule itself. Okay. So this is the three main important motion for us to describe the motion of the gases. Okay, so let me erase this one. Alright, this one as well. Okay, this one can be erased. Alright. Okay, so let's move on to the first one. First type of gases. So we have monoatomic gas. So monoatomic gas, which is the single atom. Okay. So the structure of monoatomic gas is actually a single atom. So the single atoms such as helium, argon, all we can say that all the gases in group 18, which is the inert gas, so this inert gas does not react with other chemical materials. uh, by saying that it is only a single atoms. Okay, so this is what we call the monoatomic gas. Alright, so let's say I have how to describe here. So let's say I have a three-dimensional space. So let's say we inscribe this gas inside a container. So this is a container, which is the three dimension, of course. So this is the x direction, and this is the y direction, and of course this will be z. Okay, so let's say, so since the monoatomic gas is a single gas, so there's no rotation, and since it is a single gas and it cannot vibrate by itself, it cannot be vibrated by its own, and it cannot rotate by itself. So hence monoatomic gas consists only the translational motion, which is the linear motion. So it consists of linear motion. So there are three probability direction which the gas can move, which is the x direction and y direction, and finally the z direction. So we can say that the degree of freedom for the monoatomic gas is actually 3, which is the translational motion. So this is the degree of freedom for monoatomic gas. Alright, so let's move on to diatomic gas. Okay, so let me just erase this one. So this one as well. Okay, so let's talk about diatomic gas. So what is the structure, what will be the structure of diatomic gas? So diatomic gas, of course, we know is actually the two atoms which is bonded together, as we learned from chemistry. So this diatomic gas, we have hydrogen gas, chlorine gas, or even iodine gas. Okay, so this is the diatomic gas. Okay, so let us inscribe this diatomic gas in the container again, as we inscribe from the previous gas, which is monoatomic gas. So let's say I have y direction, x direction, and z direction. Oh, I should draw it straight. So let me draw it again. So this is my y direction, and this is the x direction, and this will be the z direction. So this is my diatomic gas. Okay, so same, the diatomic gas, we know that it consists of three translational motion, which can towards the z direction, and of course x direction, and finally the y direction. So we have three translational motion. Translation, okay? So plus, so we can see that there are two rotational motion, which is along the y direction and z direction. And why there is no rotational motion along the x-axis? So let me explain later. So we have two rotation. So what we got is actually 5 degree of freedoms. Degree of freedoms. Okay, so this is the degree of freedom for diatomic gas. Okay, so as we talk about why there is no the rotational motion along the x-axis, so based on my research, okay, so based on my research, what I understand is the diatomic gas is actually parallel to this x-axis, parallel. So we can see that the diatomic gases, which is parallel towards the along the x-axis, so we insteadly it is always perpendicular to the y-axis and the z-axis, as we can see that the diatomic gas is always towards this direction, and the z direction is always perpendicular as well. So as for the x, basically, how should I inscribe this? Okay, so since it is parallel to the x-axis, so this causes a barrier for it to rotate. So there is no rotation for along the x-axis, and this is for the first explanation, parallel to the x-axis. As for the second explanation, some of the scientists I found, they said that the diatomic gas is actually not get excited. So since the diatomic gas not get excited, hence it does not include the rotational motion along the x-axis. So it means that if we increase the temperature at higher temperature, like much more high, which is around 1000 K, so there will probably a rotational motion along the x-axis. So this is based on my research. Alright, so let's move on to polyatomic gas. Oops. Okay, so let me erase this one. Alright, let me scroll it up. Okay, so let's move on to polyatomic gases. Atomic gases. Oops, okay. So polyatomic gas is actually the gas which consists of two or more gases. So for example, we have ethene, not ethene, should be ethane, which is CH4. Okay, the structure for ethane is actually like this, just like so. Okay, as we simplify it, draw in a simplified structure, so what we got is actually like this kind of structure. Yes, this is the ethane. And what about SO2, sulfur dioxide? So we know that sulfur dioxide is actually okay. Oh no, not sulfur dioxide, should be sulfur trioxide. Okay, so sulfur trioxide, what we got is actually like this. Some sort of this structure. Okay, so yeah, same as the, oh wait. Oops. Okay, so some kind of this structure. Alright, so this is the polyatomic gases, which is two or more gases, two or more atoms attached together. Alright, so let me draw again. So this will be our polyatomic gas. So let's take the sulfur dioxide as the sulfur trioxide, sorry, as the example. Okay, so same, we inscribe this sulfur trioxide in the container. Okay, so I have sorry, so this one will be the y direction, and this one is x, and this one is z. Okay, so this is my, okay, let me use another color so that you can see it clearly. So this is my polyatoms. So this is the, okay, so this one will be the attachment. Alright, so as for the first one, we know that whatever types of atoms, there will be a translational motion, which is towards all the directions, which is x, y, z. So we have three translation. Okay, so what about rotational motion? And as we can see that if the polyatomic gases is about to move towards this z direction, and we can see that it is able to rotate along the z-axis. So as for the x-axis, it is also able to rotate along the x-axis. And if it's wish to move upwards, which is the y-axis, so it is also able to rotate along the y-axis. So we can conclude that there is three translation as well as the three rotation. So three translation and three rotation, and finally we get 6 degree of freedom. Alright, so this is the degree of freedom for polyatomic gases. Okay, so we haven't talked about the vibrational motion, so we will talk it now. Okay, so let me conclude the theory as I mentioned just now. So this time we add another factor, which is the temperature factor. temperature factor. Of course, the motion for the gases is mainly affected by the temperature. Okay, let's wait. So this is the type of atoms which have the mono, and this is the di, and this is poly. I write it in shortcuts. So let's say I have a type of motion. Alright, so this is the translation, and rotation, and finally the vibration, which we haven't discussed about it. So this is the translation, rotation, and finally vibration. So this, okay, let me draw a line. Okay, so oops, never mind. Okay, so this is the type, and this is the mono. Okay, okay, so as for the translation, we know that for the let's go through for the monoatom, and for the translation for the monoatomic, so whatever low or high temperature, so this go for this same goes to the diatomic as well as the polyatomic. Whatever low or high temperature, so this will be 3 degree, and this 3 degrees, as well as for the polyatomic, which is 3 degree. Alright, so this is for the 3 types of atoms. Whatever low temperature or high temperature, there will be a 3 degree of freedom, which is represent three type of the direction, which is x, y, z for translational motion. Okay, so let's go through the rotational motion. Okay, let's talk about the monoatomic first. Okay, so as for the monoatomic, as I mentioned just now, there's no rotation and vibration even at very high temperature. So the monoatomic consists only the translational motion. So this one dash and dash. There's no rotational motion and vibrational motion. As for the diatomic gases, the rotational motion only exists if the temperature exceeds the room temperature. So this will be 2 degree. So this 2 represent the degree of freedom for the diatomic gases. As for the vibration occur only if the temperature is about 1000 Kelvin. So this is the condition which must be achieved. Okay, so in order for the vibration for diatomic to occur, so this same goes to the polyatomic, and as the temperature exceeds the room temperature, I write it in shortcut. Okay, so the rotational motion we have for the polyatomic atoms is actually 3 degrees. Okay, so the vibration motion, same. which is 1000 K. Alright, so this is the condition for the temperature for every motion. Okay, so at as we can see that at 1000 Kelvin the vibration occur for only diatomic gases and polyatomic gases. So as for the rotational motion, in order for the rotational motion to occur, the temperature must exceed the room temperature. So for the diatomic gases and as well as polyatomic gases. So this translation, even at low or high, we always have the 3 degrees of freedom, which represent 3 types of direction for 3 types of atoms. So this is how we determine the type of motion based on the condition for the temperature. Alright, so let's move on. So let me erase this one. So we're still in the parts of degree of freedom and the equipartition of energy. Okay, so we have done for degree of freedom, so let's move on into the equipartition of energy. Partition of energy. So we have principle of equipartition of energy. So principle of equipartition of energy actually states that when a gas system is in thermodynamic equilibrium, okay, the average energy per molecule, so this is our keywords, per molecule. Alright, per molecule for each degree of freedom, is actually half kT. Okay, so the principle of equipartition of energy is actually states that when a gas system is thermodynamically equilibrium, which the heat does not changes frequently, so the average energy per molecule for each degree of freedom is actually half kT. So this is the statement for principle of equipartition of energy, which describes the average energy for one molecule. Okay, so let's continue. So the formula for the total energy or for F degree of freedom of molecules. So the total energy what we got is actually equals to F over 2 kT. Okay, so wait. Wait for a second. Alright. So, oops, this one should not be the molecules, is molecules, and this of a molecule, so this means one molecule. This is the total energy for only one molecule. So this total energy we observe from this formula. So the energy is actually depends on the degree of freedom and the temperature sorry. Okay, okay, so since we have 3 degree of freedom for mono and 5 degree of freedom for diatomic gas, and 6 degree of freedom for polyatomic gas, so the total energy for monoatomic gas is actually 3/2 kT. As for the diatomic, the total energy is actually 5/2 kT. As for the total energy for polyatomic gas, we have 3 kT. Since 6 divided by 2 is actually 3, so the total energy is actually 3 kT. So this is the equipartition of energy for each type of gases. Alright, so we have done for this equipartition of energy. So let's move on to our last parts for this chapter, which is the internal energy. Internal energy of ideal gas. Ideal gas. So from the previous video, we have discussed a bit about the difference between the real gas and the ideal gas. So let's explain again at here. So what's the difference between real gas and ideal gas? Okay, so as for the first one, as we discussed from the previous video, we said that the ideal gas actually obeys all the 3 laws, all the gas laws. So all the gas law, which is the Boyle's law and Charles' law, and finally the Gay-Lussac's law. And while as for the real gas does not obey all the 3 laws. So the real gas does not obey all the 3 laws, but sometimes they obey one of these 3 laws, or two of 3 laws, but not complete all 3 laws. So that's why the real gas is always deviate from the ideal gas. Okay, so let's move on for the second difference. So as for the second difference, we said that from the previous video, the intermolecular forces, between ideal gas, between molecules of ideal gas can be neglected, but but the real gas does not. It means that there's no how should I set that? So the intermolecular so the intermolecular force between the real gas actually cannot be neglected, and as for the ideal gas can be neglected, as we said that from the previous video, the assumption of the kinetic theory of the ideal gas by saying that the collision between the gases are perfectly elastic. It means that there is no intermolecular forces between the molecules. So as for the real gases, there are the intermolecular forces that which cannot be neglected. So this is the difference between the ideal gas and the real gas. Alright, so let's move on to next parts. Okay, so let me just erase this one. Alright, so this one as well. Okay, so before that, I have to discuss about hydrogen gas, helium gas, and finally nitrogen gas. So these three gas, okay, so let me so these three gas is actually almost behave as ideal gas if in the condition of low pressure and high temperature. So at low pressure and high temperature, so hydrogen, helium and nitrogen gas is behave almost like the ideal gas, which is the collision is perfectly elastic and the intermolecular forces can be neglected. Okay, so this is the approximation for hydrogen, helium and nitrogen if the condition is at the low pressure and high temperature. Alright, so let's move on to the next parts. Okay, so let's discuss about the real gas first. So let us discuss about the total energy for real gas. So as we discussed just now, by saying that the intermolecular forces for the real gas actually cannot be neglected. So since the intermolecular forces cannot be neglected, so it's this account for the potential energy. There's excess of potential energy in the real gas. So the total energy for the real gas is actually equals to the potential energy, which is due to the intermolecular forces plus the kinetic energy, which is the kinetic energy, which is account for the motion of the real gas. So this is the total energy for the real gas. Alright, so let's move on to the ideal gas. So as for the ideal gas, total energy of the ideal gas. So we discussed just now from the previous parts, the intermolecular forces for the ideal gas is actually can be neglected. So it means that no intermolecular forces and hence no potential energy. So the total energy for the ideal gas is actually only the kinetic energy. So this kinetic energy, we know that the kinetic energy for the gases is actually depends on the temperature. So as the temperature increase, the kinetic energy gained by the ideal gas is also increased. So there are three types of gases we know, which is the monoatomic gas, diatomic gas, and finally the polyatomic gas. So it means that the total energy is actually depends on the degree of freedom. So this one is actually divided by, okay, so this is F over 2 kT, which is the formula which came from the equipartition of energy. So as for the monoatomic we have 3, and for the diatomic we have 5, and finally the polyatomic we have 6 degree of freedoms. Alright, so this is the kinetic energy for the three types of gases, so which is actually equals to F over 2 kT. Okay, so have to note that if the kinetic energy for the ideal gas depends on the temperature, it means that the internal energy, so this one should be the internal energy. So the internal energy, or we can say that the total energy of the ideal gas is also depends on the temperature. So this temperature is the utmost importance for us to determine the internal energy of the gases. Alright, so yeah, this is the kinetic internal energy. So have to note that this is actually for only one molecule, of course. Okay, so let me just write it here. Okay, so what if I need to find the internal energy? Oh, before that, I have to note that there's another thing. So as we discussed about the internal energy based on the temperature of the gas, so if the heat supplied to the systems, so the internal energy is actually increased. So as for the heat release, so let's say the heat leave the system, so the internal energy for the ideal gas is actually will decrease. So it means that the internal energy depends totally on the temperature. Alright, so let's get back to here. Okay, so let's say I have a 1 mole of gas. 1 mole of gas. So what if I wish to find the internal energy for 1 mole of gas? So this, we know that F over 2 kT is actually described for one molecule. So we know that 1 mole of 1 mole of the ideal gas, so 1 mole is actually equals to Avogadro constant of atoms, which is 6.02 times 10 to the power of 23 atoms. So 1 mole have 6.02 times 10 to the power of 23 atoms. So if I wish to find the internal energy of the 1 mole of the ideal gas, so the total energy for me is actually equals to F over 2 kT times the Na. So we know that K is actually the constant of the Boltzmann constants. So the Boltzmann constants is actually equals to R over Na T times Na. So this R over Na is actually equals to the Boltzmann constant. So with this one can be cancelled. So the total energy or the internal energy for the 1 mole of gas is actually equals to F over 2 RT. Alright, so this is the total energy. So what if I have the N mole? So let me just scroll it here. So N mole. So I have the N mole. So our total energy is actually equals to F over 2 nRT. So this is the one molecule. Okay, so let me highlight it. So this is the one molecule. Okay, so this is the 1 mole of gas. And finally, this is the N mole of gas. So let me just scroll it down here. So this is how we determine the internal energy for one molecule, 1 mole of gas, and the N mole of gas. So we have to note that the internal energy is based on the degree of freedom, which is the type of the gases, and finally the temperature of the surrounding, which is the utmost important for the internal energy of the ideal gas. Alright, so we have done for the chapter of the kinetic theory of gases. So I think we stop here and we'll see I will see you in the next chapter. So oh, not the next chapter, there is still a revision video. Alright, so if there are any questions need to be asked, and please comment below below this video. So I'll see you next time. So thank you, bye.